So this is our third video in the study of representation theory of finite groups. We will be discussing one of the most important theorems in the study of representations. But let me first start by summarizing what we've done so far. In the first video, we motivated the study of representations by saying that roughly the symmetries which corresponded to physical actions. So these are the actions you actually do on a system, physical actions on a system. This set of questions can be translated in some way to understanding the nature of a linear operator. Which we could use to decompose our vector space. Then in the second video, we gave a much more careful definition of a representation, and we introduced it as a group homomorphism. So a representation was a group homomorphism. From a group homomorphism from the group to the set of invertible linear operators acting on the vector space V. Now let me first say, let me repeat what I said earlier in the second video but did not emphasize, which is that you will often hear, see, read mathematicians and physicists sometimes, in fact a lot of times, call this vector space here also the representation. And I made a very brief comment and say that I'll be a bit picky and call it the representation space. And although it ultimately makes very little difference, keeping this difference in mind will help a lot when we come to understand some theorems and some proofs. It's often a good idea to remember that the representation is a group homomorphism and a map from the group to a set of invertible linear operators, and it's not defined as a vector space that's acted upon by this set of invertible linear operators. Although if you're not very careful about such a distinction, you can often not see the harm in doing that. But it will come back to bite you. And in fact, what we'll start with in this video, it's very important that we keep in mind the distinction between the vector space that's acted upon by the set of invertible linear operators and what we call the representation. So let's begin by proving a few lemmas that we'll need for our big theorem that we'll prove in this video. So here is an important lemma. So lemma, I'll call it a lemma. It's a lemma to me. So let F be a homomorphism of a representation then the kernel of F, which is the set of vectors in V such that F acting on V is 0, and the image of the homomorphism, which is this way, are sub-representation spaces, I should say, sub-representation spaces of V and W, respectively. Okay, so we'll now clearly see why I made this distinction earlier between a representation and a representation space. So what do we need to show? So what do we need to show? So remember how we defined a sub-representation. I think in the second video I was a bit careless, and I called the representation space a representation. But we say that our sub-representation, a sub-representation space is a subspace of the representation space that is stable under the action of the group. In other words, when I get a representation of the group and act by any operator in a subspace of my vector space, the outcome is another vector in the subspace of the representation space. So what we need to show is that if I have phi that goes from G to GLV, for example, and if I have psi that goes again from G to GLW, notice that phi and psi are the representations, and V and W are my representation spaces. Then what I need to show is that, for example, the action, the representation phi that acts on the group G to give phi G, that will act on V, where V is an element of the kernel of F, then we want to show that this is also in the kernel of F. So it's to see how helpful it is to distinguish between the representation space and the representation. It just helps in making our thought processes a lot more clear. So how do we do this? Well, we want to use somehow the fact that F is a representation homomorphism. If it's a representation homomorphism, then we had a condition on F. So remember, a representation homomorphism meant that if I have two representations, in our case here we have, let's say we have phi, then F goes from V to W. So if I have, let's say F acts on V, let's say twiddle, where twiddle is in V. F acts on twiddle, and it will produce some vector in W, and then psi will act on that vector. That's the same thing as saying that I have phi, the representation phi, that acts on V twiddle, and then F acts on the result. So this was this was our definition of a representation homomorphism. So this is condition for representation homomorphism. So we want to use that. So how do we do that? Well, let's get psi. So this psi G is a invertible linear operator, and it's going to act on this. Notice that psi was a representation from G to GL of W, and F is a map from V to W, so we need to act on. After we act on by F, we need to act on by psi. Because F is a representation homomorphism, this means that we can do this. Now, V is in the kernel of F. So V, I remind you, is in the kernel of F. So that means that psi of G is this, which is 0. And that should equal to phi of G. Now, let's rename that to be V prime. So phi of G acting on V is another vector V prime. And then F will send V prime. So what will it send it to? Well, by the calculation here, it sends it to 0. Well, what does that mean? It means that V prime is in the kernel of F. Okay. So by their definition of what a sub-representation space is, the kernel of F is a sub-representation space. In other words, it's stable under the action of our representation phi. Now let's look. So the kernel of F is a sub-representation space. All right. And the second part was looking at the image of the function f. This, we claim, is a sub-representation, representation space of W. This is again a straightforward application of definitions. So we know that here now V is not in the kernel, it's just some function, it's just some vector in the vector space V. So let me call that V double prime. V double prime is in V. F acts on V double prime, and then this is obviously in the image of F. So in order to show that the image of F is a sub-representation space of W, we must show that the action, that it's stable under the action of psi of G. In other words, psi of G acting on V of F is again in the image of F. Again, trying to be careful here. We have that psi of G acting on F of V using the definition of what a group representation, a representational morphism is supposed to be. We have the following, and we can then call this V triple prime. So V triple prime, and V triple prime is in V, vector space V, and then F acts on V, which is in the image of F. So of course this implies that psi acting on F of V is in the image of F. Okay, so we've now shown that the kernel of a group representation homomorphism and the image of the representation homomorphism are all sub-representation spaces. There are analogs of these theorems in group 3 also. If I have a group homomorphism from a group G to H, the kernel of that homomorphism is a subgroup, and the image of that group homomorphism is a subgroup in the image of that group homomorphism. Okay, so a few definitions. So we have an irreducible representation. So a representation is irreducible if it is non-zero and has no proper non-zero sub-representations. Okay. This can be translated into a statement about the representation space. So the idea here is that if you can find any sub-representation of this representation, in other words, if there's a vector space that this representation acts upon that's a subspace of the original vector space, then that subspace is either the zero vector space or the whole vector space itself. All right? And another notion we'll need for this important theorem that we'll state later on is the direct sum representation. So again, let V and W be two representation spaces. Then the direct sum representation space is given by V direct sum that with component wise G action. So in other words, we have the invertible linear operator phi of G, where G is in the group G, and it's going to act on this ordered tuple, and the result is going to be phi of G, phi of W. Another definition: a representation is indecomposable if it is not a direct sum of proper sub-representations. So clearly, if you look at the definition of an irreducible representation, so it's a non-zero. It's a sub-representation that's non-zero and has no proper sub-representations. And then we have the indecomposable. That's not a direct sum. So clearly, an irreducible representation is indecomposable. Okay, it's indecomposable because it has no proper sub-representation, so it can't be a direct sum of anything that's proper. But the converse is not true. An indecomposable representation need not be irreducible, okay? Because it has proper sub-representations, right? I mean, by definition. So if it has proper sub-representations, well, it can have proper sub-representations, and if it can have proper sub-representations, then by definition it can't be irreducible. Now, in the simple cases that we deal with, for example, in your undergraduate career, and especially for any sort of group that you might meet, as let's say as a physicist, the notions of irreducibility and indecomposable coincide. You need to be pretty advanced before these distinctions begin to make much of a difference. And we'll certainly in these videos deal with examples where the notion of indecomposable for the most part will coincide with the notion of irreducible, namely that if it's indecomposable, then it probably will be irreducible. If it's irreducible, it's indecomposable. But okay, it's important to note that the two notions are not equivalent. So here comes our important theorem. So remember that we had the equations of motions, and we argued that there were, in our physical system we had linear oscillators. And we argued that there were coupled linear oscillators, and we argued that there was a coordinate system in which the equations of motions decoupled. And we argued that this meant that the vector space in which that contained the vectors which contained our equations of motion somehow divided up into eigenspaces of some linear operator that was diagonalizable. So here is a important theorem which tells us that at least for finite groups, this breaking up of our vector space is always possible. In fact, the breaking up of our vector space will always be possible, and it will break up into irreducible representation. And this is really important because it makes the study of representations a very tractable problem. It turns a problem of studying representations into a problem of studying essentially linear operators and how they it allows us to say that all we need to care about is the vector space, basically. And if I can understand how it breaks up, then I've understood everything about the irreducible representations of my group. And if I understand the irreducible representations of my group, then what more can I ask for? Because I can build any other representations by combining these irreducible representations. So here's a theorem. It's called Maschke's theorem. I think that's how you pronounce it. Maschke's theorem. So I'm going to change colors. Put this in a bubble because it's really important. And I'll write it in red. So let G be a finite group. So this is the first instance in which we're now using the finiteness of our group. And this is also the first instance in which the fact that we have a field whose characteristic is co-prime to the order of the group will come into play. So let's say we have a G that's a finite group, and K is a field. Later on, I will ignore this field stuff because I'll choose a field of characteristic 0, namely the complex numbers, and then I won't have to mention I won't have to keep mentioning this next phrase of characteristic coprime. This is what I will avoid later on because I'll choose later the complex numbers. Coprime to the order of G, and let V be a representation space over K, and U a sub-representation space. Then there exists a W such that V is isomorphic to U direct sum W. Now, hopefully, what you'll see as I progress is why it's useful to keep distinguishing between the representation space and the representation. Nailing this point on the head because it's rarely ever done, and at least I find it useful to always keep doing this. It keeps my head straight. So what we'll do is that let's do it this way. Let's proceed this way. So let W be any complement to U in V as a vector space. Okay, the complement need not be a representation, but we can certainly do that. And so then along with that, we'll pick a projection pi prime that will go from V to U along W prime. So what this means is that this implies that for all V in big V, we can write our little v uniquely. We can write it as this. I'm not sure about uniquely, but I think we can definitely write it this way. With u, little u in big U, and little w in big W prime. Now we're going to do something that I don't like because it comes out of the blue, but we'll try to motivate it. This is one of those things where you define something that seems mysterious but ends up being really helpful. So define pi v, not pi prime, but pi v, and it's going to act this way. Summation g, and I'm going to do this. Okay, so I have a representation that I've chosen, phi. Again, usually what you'll see in books and texts is that they'd probably, rather than writing, let's say, phi of g acting on v, because for me phi was the map from G to GL V, people will usually write something like G times V. And okay, as long as you know what you're doing, that's okay. But you know, I like to think of G as being in the group, and if it's in the group, then it can't act on a vector. So I need to produce the mapping from G to GLV, and then that result in GLV acts on the vector space. But anyway, again, it's just me trying to keep things orderly in my mind. But very few people do this anyways. Okay, so what is this doing? Oh, sorry, there's a mistake here. Pi prime is our projection. So what is this doing? So let's investigate this before we move on. So let's remember that V can be written uniquely as U and W. So what we have, and by the way, we now see why we need the characteristic of K to be co-prime to the order of the group G, because you can see later on that we'll be summing things, and we don't want to get 0 when we add this sum. Okay. So what is this doing? We investigate. Let's investigate the summand. So we have sigma of G and G, and we have our representation, and it's going to act like this. U plus W. Okay. Well, the representation is linear. Well, that's nice. And so we'll get that, and we'll get now pi prime is a projection. In other words, that this is going to be 0. And what does this give? So what does this give? So here is where it's really, really helpful to keep things straight between the sub-representation space and then the representation. So remember, the sub-representation space was stable under the action of our group G. So U was defined, U by assumption, U is a sub-representation space. In other words, it's stable under the action of the group. So what that means is that phi of G acting on U is again in U. Okay. So when the projection operator acts on this thing here, the result is again in U. And what that means that if I restrict this projection operator to the sub-representation space U, it acts by the identity. So pi acts by the identity, right? It has to, because this is phi of G acting on U is already in U, and pi projects to U, but we're already in U, so we have to act by the identity. And so we're left with that. Okay, but again we have a representation which is a group homomorphism. Remember, so here's how, like, hammering this point between the group homomorphism, the representation space. They're not the same thing. Here I'm using now the fact that the representation is a group homomorphism, and so in particular it's equal to that. And of course it gives the identity, and then we're left with this over G of U. And of course we now remember that there was a 1 over G prime here. 1 over G, sorry, not G prime, just G. Okay, and our field K is co-prime to the order of G. Here's where it comes in. And so in particular, this is just equal to U. So in fact, this, so let me write this more neatly. In fact, what we defined earlier is just a projection onto the sub-representation space, big U. Okay, so we now have, pi projects out the complement of U in any vector V in that. Okay, now, so remember we're trying to prove Maschke's theorem. Maschke's theorem says that if you give me a sub-representation space, then I can find another representation W such that the direct sum of that other representation space and the one that I have already gives me the whole representation space V. So what is the reasoning behind what we've defined? So we know that any vector W in W prime is in kernel of pi. So now you see where we're going. We proved that the kernel of a representation homomorphism is again a sub-representation. So what we want to show is that, for the next step, that the pi is actually a representation homomorphism. And then by the lemma we proved earlier, the kernel is a sub-representation space. Okay, so let's prove that the pi that we have is a representation homomorphism. So what does that mean? It means that we need to prove that pi So need to prove. Pi is a representation. Homomorphism. And then this will imply by lemma that the kernel of pi is a sub-representation. Space. Okay, so in particular, what we need to show is that pi of phi of, let's say, g acting on v is equal to phi of g acting on v. Now, why didn't I need to? So notice that I did not need to define another representation, let's say psi of g here, because, well, why? Because this is in U, and U is a sub-representation space, and therefore it's stable under the action of phi. So the general definition of a representational homomorphism simplifies to something like this. So we do this calculation. So we have summation all in G and projection onto sorry, let me make this H. This is H. Let me turn this to H. Let me turn this to H, and H is an element of G. And so this is equal to sum over G prime G So what I did was I redefined my summation. Rather than summing over G, I'm summing over G prime. And I'll leave you to figure out why I did that. It should be very easy to figure out. And so there is no sum over H. And so I can take this outside. Okay, and that's equal to phi of H pi of V. So this means that pi is a representation homomorphism. So pi is a representation homomorphism. So we have that W, as a consequence of this, W, which is the kernel of pi, is a sub-representation space. Okay. Now, by the rank nullity theorem, we then have Maschke's theorem. Why? So now we recall the rank nullity theorem. So we have the dimension. Let's have an operator t, which I will call. Well, I'll stick with t for now. Well, let me go straight to pi. Dimension of pi. Dimension of the image of pi plus the dimension of the kernel of pi should equal to the dimension of v. And of course you can see that what this gives us is that u direct sum kernel of pi is v, and so we can set w equal to the kernel of pi. And so the kernel of pi is the other subrepresentation space that we were looking for. Now, what is a corollary? A corollary is very important. So the corollary of Maschke's theorem. This is what gives us hope to continue our study. Which I'll put in another color. So it's very important. If G is a finite group, now the finiteness of the group is coming in. This is why this video is on representation theory of finite groups. And K, a field, again of characteristic coprime to the order of G, then any finite dimensional representation of G over K is a direct sum of irreducible representations. Now, why is this true? I'm not going to write this out, but I'll just say it out loud. So we have already proved that given a sub-representation space or a vector space V, we can always, by Maschke's theorem, find another vector space which turns out to be a sub-representation space also in such a way that the direct sum of these two sub-representation spaces gives us the original vector space V. Now, these sub-representation spaces may be reducible. If they are reducible, then we apply Maschke's theorem again to each direct summand. And we do that iteratively or inductively on each time until we end up with a sub-representation space that's not reducible. And once we've done all that, we'll end up with the direct sum decomposition of the vector space V, in which our representation breaks up. And so what this means is now that in order to study the representation theory of finite groups, what we need to understand are the irreducible representations. Of course, the elephant in the room is that we're not going to say anything about indecomposable representations. As far as I know, for the undergraduate career, which I'm only interested to understand, irreducible representations are what we deal with, and because I'm a physicist, they're what I run into a lot more. I've never run into I have run into indecomposable representations, but they're not really of any importance yet in physics. So that's the end of this video. Thank you.